Oh, good morning, everyone. Thank you, Richard. This was the most generous introduction I've ever had. Forget about listing all the CV and so on. I think very much appreciated. I was actually prepared for something else, but yeah, maybe you'll hold off. So it's a pleasure to be at home, and thanks to the organizers for inviting me. I'd like to talk about joint work with my PhD student, Clemens Hutter, and my former student, Recep Gül. Now, learning of linear dynamical systems. I'm sure that many of you have followed work in the last couple of years about learning the solutions of PDEs with neural networks. So this is not about learning the solutions of PDEs. This is about learning PDEs themselves from input-output traces. You have right-hand sides and parameters, and you have excitations. And so based on these pairs, you would like to learn the structural equation itself. And the question is, what are the limits of learning the equation itself? And that actually is a topic that, at least for linear systems and partly also nonlinear systems, has been studied quite a bit in system theory and control theory and signal processing. I'll be talking about that in a second. Just to start with some applications. So there are recent papers by Koumoutsakos and collaborators. They used LSTM, RNNs for modeling of extreme events, forecasting of high-dimensional chaotic systems. Then, of course, this is a topic in reverse engineering systems biology, where you would like to understand certain biological mechanisms based on input-output traces, population dynamics, for example, the age distribution and of a population can be modeled as a dynamical system. And of course, as I mentioned, it's a classical topic in control theory and signal processing. Channel estimation, wireless communication is all about, so when you use your cell phone, then first the phone has to learn a dynamical system, namely the channel. How does it do it? The transmitter and the receiver have an agreement. The transmitter at the prescribed time sends a message that is known to the receiver. The receiver tries to infer the channel or the underlying dynamical system based on the observed signal and on the pre-agreed upon message. And learning of ODEs and PDEs. Good. Now, what are the methods that are known for system identification? There are way too many to list. So what I decided to do is to point you to the book by Söderström and Stoica in 2001, which is one of the standard texts on system identification. There are parametric and non-parametric methods, feed-forward systems only, feedback systems. I'll be talking about that a bit later. Many of these techniques are about dimensionality reduction because many of the systems of interest are of high intrinsic dimensionality. There are Gaussian process regression-based methods. The idea is that you excite the system with a Gaussian process, you observe the output, and you're trying to fit the model. Instrumental variable methods. There are offline methods, online methods, meaning that if the system evolves over time, if it's a time-varying system, then you keep tracking it. And for the nonlinear case, probably the best known in control theory and signal processing are the Volterra and Wiener theories. So there's a book by Martin Schätzen if you're interested in this topic, which is excellent. These methods are often very specific to the structural properties of the system class. And as I said, they are numerous. So what people have started doing, and actually not only recently, the first paper I could find dates back to '97, was to use recurrent neural networks, which I'm about to define on the next slide, to learn dynamical systems. The book by Mandich and Chambers on recurrent neural networks talks a lot about the dynamical richness of recurrent neural networks. The question being that what are the limits in terms of representing dynamical systems with recurrent neural networks? Probably the most visible paper in this area is a paper by Hart and others, which finds that RNNs trained with gradient descent can approximate linear systems. There are also recent two recent papers, one by Gu and collaborators and the other one by Yarotsky. That's actually Dmitry Yarotsky, who also did fundamental work in neural network approximation theory on using RNNs for channel estimation. And then I would like to mention work that is not along those lines, but still because I think it's very interesting and is gaining a lot of attention. learning of nonlinear operators with deep operator networks. So these are essentially finite dimensional sections of nonlinear operators that are learned with specific structures. So you can look at the most recent paper by Lanthaler et al. So Sid Mishra is doing a lot of work in this area. Good. Okay, so what is a recurrent neural network? So for the purposes of this talk, so the philosophy I want to take in this talk is that I would like to simplify all the way down to, I think, the simplest possible mathematical setting. So there is lots of, continuous time, and you can do these measures theoretically and so on. So I want to just take all that, cut all that out, and just work with the simplest possible mathematical setting. And that will happen to be discrete time. What we will retain is actually that we're looking at infinite dimensional systems. So that we're not going to take out because it's a core part of the theory. So recurrent neural networks are defined as follows. You have an input and an output. So think about a dynamical system. You have an input, you have an output. Input is X, the output is Y, and you have a state vector, H. And the state vector evolves. And the evolution equation is like this. Phi is a neural network. And again, as I said, we want to be as simple as possible. So we're going to use a single hidden layer neural network. So you have an affine transformation, A1x plus B1. Then you apply the Rayleigh nonlinearity element-wise, and then you have another affine transformation, A2. And then this neural network determines the evolution of the state vector as well as the computation of the output from the input. If you unfold this neural network, it looks like this. So if you go back to the evolution equation, you see if you insert t is equal to 0, you have y of 0 and h of 0 is obtained by applying the feedforward neural network to x of 0 and h of -1. So this is how it looks like. So you have h of -1, so you initialize the state vector, typically by the 0 vector, and x0, they enter your feedforward neural network. Out comes the output signal at time instance 0, and the state vector at the next evolution instance. And then you enter x of 1, and you combine it with the state vector, and so on and so forth. So that's what the recurrent neural network does. Of course, you can do this with deep networks and so on, and I'll be talking about that towards the end of the talk a bit. So that's the system that we're dealing with, and these are the two questions that I would like to address in this talk. As I mentioned, the Hart paper found that with gradient descent, you can approximate linear systems with RNNs. There is a book by Mandich and Chambers, dynamical richness and so on. What are the limits, fundamental limits on the dynamical richness of recurrent neural networks? So are there limits in terms of what structures they can represent or what kinds of ODEs and PDEs they can represent? That's question one, first part of the talk. Question two will be concerned with the complexity of this representation. So first we'll establish the fundamental limit, and then we'll ask the question, given a class of operator systems differential equations, and given the complexity of this class, and I'm going to define later what I mean by complexity of a class of operators, it is going to be metric entropy, but in a special sense. And that's also for those of you who are in signal processing and control. I would like to propose a viewpoint of identifying systems to a finite resolution. That's something that is usually not done, but I think it's something very interesting. It was started in the 1990s by control theorists, and I think it comes in handy here. So that's the complexity of operators. And what we'd like to understand is that given a class of operators and the corresponding complexity, what is the complexity of the recurrent neural networks that you need in order to represent those operators to within a prescribed error? Okay, good. So let's get started. We are going to look at partial differential equations. So this is the book by Charlie Gröchenik. The exposition on the next two slides is actually taken from his wonderful book. You have an operator L, and you have a derivative, and you have these weighting functions here, and they are x-dependent. So these are called pseudo-differential operators. And now what you do is I'm going to introduce now the while calculus. For some of you are probably familiar with this. It's a theory that was developed in mathematical physics, I guess starting in the 1940s or 50s and so on. And the reason for developing this calculus will become clear very soon. So let me go ahead. So you write the derivative of f in terms of the inverse Fourier transform. So taking derivatives in the time domain means you multiply by 2 pi I omega raised to the power of alpha in the frequency domain. Then you take this expression here, you insert it up here, and you get this expression here. So now what you do is you say, well, our sigma of x and omega has a very specific form. It is obtained from those weighting functions and multiplied by those factors omega to the alpha. So now you can go and you can say, let's replace sigma by an arbitrary sigma of x and omega. That is actually the function sigma is called the symbol of the operator. So if you do that, then this is what you get. You get the so-called pseudo-differential operator with symbol sigma. For the system theorists, this is often also called the while symbol or time-varying transfer function, and I'll be showing you something in a second. And then, so here are some examples. The easiest one is the Laplace operator. You just take sum of second derivatives, and if you go to the Fourier transform, you apply the Fourier transformation rule. So a derivative in the time domain becomes a multiplication by 2 pi omega in the frequency domain. You do it twice, you get minus omega squared. Of course, this is a Laplace operator with n independent variables. So this is actually the sum of omega 1 squares. If you have the heat operator, you have d dt minus Laplace operator, or the wave operator, you have the second derivative of t. And if you have the Sturm-Liouville operator, then you get, in the first three cases, the symbol depends only on omega. In the last case, it properly depends on x and omega. And of course, you know that if you have a 1D Schrödinger equation, time independent, then that becomes a Sturm-Liouville operator. So these are the classes of operators. Again, for the system theorists, for the first three cases, this you can think about linear shift invariant systems. And this is just a transfer function calculus that you learn in basic signals and systems classes. Okay, so now let's look at the representation theorem for pseudo-differential operators. So this is again from Charlie Gröchenig's book, which says that every decent linear operator can be represented in those two forms. Namely, and that's the first one, that's the one that we're going to work with. This function S is called the delay Doppler spreading function, and I'll tell you in a second why. You see that the essence is that you have time shifts and you have frequency shifts. So that means every pseudo-differential operator that is, whenever I say decent, I can tell you offline if you want the qualifiers. Can be written this form, or it can be written in terms of a kernel, k of t, comma tau. Now, so what does this have to do with what I showed you on the previous slide? Well, as you probably can imagine, these three are all equivalent. So if you start with Lx of t is equal to k of t, comma tau, x of t minus tau d tau. So then you can write this operator here as so what you're doing here is you fix tau and you have a Fourier transform relationship between t and f. So you write this as the inverse Fourier transform of this here, which is actually the while symbol that I showed you before. So then you can insert this here and you have LH of tau and f, you get x of t minus tau e to the I 2 pi ft df. And then you can do this. You have dt, so we have this, and then we need an e to the I 2 pi ft, and then that should be a df, and then this is our x hat of f, and that's precisely what we had on the previous slide. So that's this sigma x of omega is this time-varying transfer function, or LH of t and f. So why am I showing you all these three different equivalent representations? Well, this actually to connect to PDEs, but this is actually what we're going to work with, this delay Doppler spreading function. So again, for the system theorists, you can think of this kernel here as an extension of the impulse response. So if this is a shift invariant system, then this kernel would depend on tau only. But since it's a general time-varying system, it depends on t. S and this spreading representation is what we're going to work with y. So as you can probably already guess, what we're going to ask is, can a recurrent neural network represent or implement time shift operators and frequency shift operators? And if yes, and if you can also implement linear combinations of time shift and frequency shift operators, that could actually be the answer to the question we're asking. It turns out this is actually quite simple. If you look at the state evolution equation, you can probably guess that it's rather easy to construct a time shift, or in fact a convolution operator, and we're going to construct those RNNs. The modulation operator is a bit more difficult, and then you have to put things together and so on. Yes.
The change of notation there, the f and the x.
Yeah, right. So this is just okay. Yeah, I use a different notation because this is what it's used in system theory, and so sigma of x and omega corresponds to this at h of t and f. So x is t and f is omega. That's fine. This is what I'm used to. So good. Okay. So anyway, so that's what we're going to do. And well, a time shift is a special case of the convolution. So as I said, we are going to be as simple as possible. We are going to restrict ourselves to systems or operators mapping R to R, so no RD to R. We're going to restrict ourselves to discrete time, causal systems, and the systems accept right-sided inputs. And in a special case or an example is a linear time-invariant operator that looks like this. So the first result I'm going to show you is that you can realize such a convolution with a recurrent neural network. Since you can realize a convolution, you can realize a time shift, because the time shift is a special case of the convolution. Yes.
Can you imagine why you're going to rest the causal reverse, but are you allowed to restrict like this? Does it make sense to restrict to causal operators only?
You can actually do a baby-set restriction, then you get a factor of 2 in some of the covering numbers and so on.
Okay.
It's for all. So there's one, actually, there will be one point in the talk where I will make an assumption of linear shift invariant systems where I explicitly say this is conceptual, and by conceptual I mean we don't know how to do the general case. All the other restrictions, actually, we know how to do it with them. It's just for simplicity.
Did you say that the linear the L operator is now a scalar that acts only on the reals, or like you did that now?
Yeah, so you're mapping a sequence of real numbers to a sequence of real numbers.
All the differential operators are not acting on RD, but on R.
Yeah, so just for simplicity, we can have the constructions for RD to R, but we're doing this for simplicity.
The time component of a heat equation you still have as a separate. I mean, you need at least 2 variables to.
Yeah, you need at least 2, right? The T and
the T is sort of still there, and then the state space is just a one-dimensional one.
Yeah, so you just get a higher dimensional state vector if you do RD to R. And for each component in the input, you need to construct a network, but you can actually do it. So yes, I understand, of course, for the heat equation, you have n+1 independent variables, likewise for the wave equation and so on. So we are not looking at RD to R for simplicity. But we're looking at R to R because we're only interested in the structure. We want to realize those time frequency shift operators. Is that okay?
Now, sure, yeah, thank you.
Okay, good. Just all for simplicity. Okay, good. So we are going to work with the spreading representation, and we are going to look at a fully discrete version. Again, this is for simplification. And we are going to look at a total of D times F time and frequency shifts, simply because we also want to have a notion of size of the operator, and size is the number of time and frequency shift components in the spreading function, and that will play an important role on the next few slides. Okay, so that's so causal, discrete time, R to R, and so on. These are all for expositional simplicity assumptions. And now we get the first result that I announced. That is, there exists a recurrent neural network with input-output relation equal to a convolution. So this is the convolution kernel. These are the time shifts. And the size of the network in terms of the number of non-zero weights is of the order of the length of the impulse response. as I told you, that's rather easy to construct. And I wrote here that the proof is constructive, and that will be important later on, because one of the important questions here is that if you have trained a neural network to learn an ODE or a PDE, can you read out the differential equation from the network? The answer is, in general, not uniquely so. But our constructions are such that you actually can uniquely read out the ODE and the PDE. So you have to ensure that by way of construction. In general, you cannot. Why? If you have a feed-forward neural network, it was mentioned yesterday, I think Remy mentioned it in his talk, there's a lot of non-uniqueness. If you have ReLU networks, you have what we call the big null networks, so networks mapping every input to 0. And then if you have such a nonlinearity that has this ambiguity or non-uniqueness, then you cannot go back and forth between the function and the network. There is one case, and that also Remy mentioned, the hyperbolic tangent nonlinearity. So that's a paper 94, Pfefferman, who looked at multi-layer networks and uniqueness, and has these 5 conditions on the network architecture. If those 5 conditions are satisfied, you have uniqueness between the mapping the function to the network and back, up to permutations of nodes and sign flips of input and output, because hyperbolic tangent is an odd function. You can actually show that you can do away with these 5 conditions and you can still get uniqueness. So for hyperbolic tangent, you get uniqueness. For ReLU, you do not get it. And you have the same problem here with RNNs. So the construction is such that we don't run into non-uniqueness problems. So if you train these networks with that architecture that is developed in the proof, you can uniquely read out your ODE or PDE. Good. The second result is RNNs can realize, yes.
Read out the ODE or PDE. I mean, so you're assuming that the solution is of a convolutional form then.
This is for, yeah, if you only have, I'm going to get to the general case.
Lots of PDEs, which the solution is not just a convolution.
Right, yeah, so this is just for in the Weissenbuch calculus. This would be sigma x of omega depends only on omega. So that's just transfer function calculus for now. But now I'm going to show you the modulations, and then I'm going to put everything together. And then you can have this statement for general sigma x of omega, so for general pseudo differential operators. Okay, so that's for now, it's so for this, it's only if sigma of x and omega depends on omega only. Okay, so there exists an RNN with order f non-zero weights, and f is the number of frequencies that realizes modulation as input-output mapping. So this is a multiplication operation. This is a bit less obvious to see that you can do this with an RNN, and you actually have to fiddle around a little bit with periodicity and so on. And again, the proof is constructive, and not only constructive, but constructive such that you can uniquely read out whatever you have learned. And then you put everything together. If you can realize convolutions, you can realize time shifts. If you can realize modulations, then you can realize time frequency shifts. So you have the Heisenberg group underlying, and then you can show that there exists an RNN with order df non-zero weight. So df is the size of the spreading function, the number of time frequency shifts, that realizes exactly pseudo differential operators. So that's the universal realization theorem. All the weights are real numbers. So nothing yet about finite resolution. You need to use it in state sharing across time and frequency shift subnetworks and exploit the linear combinations of RNNs, or again, RNNs. So there's some effort into constructing these things. And again, the architecture is such that you can uniquely read out the PDE. But there will be more to this. In the second question that I announced, we are going to address the issue of complexity of learning PDEs and complexity of RNNs. And there, this construction of the architecture we have will be such that the number of bits needed to represent the architecture is dependent of the approximation error, and you only represent your weights according resolution. I'll tell you in a second. So there are two aspects in this constructiveness of the proof. Yes.
So this is an exact representation.
Yes.
Not an approximate, like for every epsilon.
Correct. That's why we call it the universal realization theorem rather than approximation theorem.
And it is for any D and F, yeah.
Yes, it's for any D and F, and it's linear PDEs and RNNs. If you have nonlinear PDEs, it's a different story. I'll be commenting on that towards the end of the talk.
And the network, the activation is any?
Not any, it's ReLU. Everything is ReLU here. If
there exists a ReLU RNN.
yeah, there exists a ReLU RNN. Yeah. Francis?
I think you say it's exact, but you put to self this situation where you have band limited and time limited problem. So if you were to look at a true signal, a true system, you would use location and then get an approximation, not the exact result.
So there is you can do all this in continuous time. Then your RNN is defined as the evolution equation is y of t, and the derivative of h is phi x and h of t.
You get an approximation with a finite size.
Right. And then you have two things you can do. You can look at the approximation of a PDE over a compact interval, or you can look at all of R. And then in the latter case, you need what is called a fading memory condition. But you have actually, even for nonlinear PDEs, you can show that there exists and so on, and approximation to within accuracy epsilon, but it's not like a universal realization theorem like here. It's an approximation theorem, but either compact support or fading memory conditions. So you have to restrain.
Last question. So I'm going to discuss the stability of the operator going because in RNNs, my impression was that if you iterate the same system over and over, and you get instabilities, but you either converge to zero or explode.
Yeah.
You take this to account at one point?
Yes, actually in the second part of the talk where we quantize and then if you don't want error accumulation, and so this would actually be excellent question. Anything else? If not, then I can move on. Second part of the talk. What can we say about the complexity of the RNNs and the complexity of the operators they are to learn? In particular, here is the viewpoint that I would like to propagate. That is the following. If you think about system identification, think about the convolution operator, and you have inputs and outputs, and based on input-output observations or one observation, you want to infer the convolution kernel. So how do you do this? Well, it's very easy. You do it in the frequency domain, and you know that convolution is diagonalized by the Fourier transform, and you're done. It's clear how it should be done. You take the Fourier transform of the output, you know the input, and you divide pointwise in the frequency domain, and you have the transfer function of your system. You take the inverse Fourier transform, and that's it. So what I would like to say is that in practice, this is not how you can do it, because you can never observe real numbers at the output. So the viewpoint I would like to propose is that suppose you can observe the output to within a certain number of bits. So if what I mean by this is, suppose you have a real number in the interval 0, 1, and I tell you, well, you cannot have access to the real number. You can only observe 3 bits, let's say the first 3 bits of that real number. So what will be the accuracy to within which you can actually approximate that the correct real number? It will be 1/8, right? If you observe the first 3 bits. Now here, you can lift this to a new dimension. That is, you want to identify a convolutional operator, and you are allowed to only look at finite resolution versions of the output. So what we will do is, we'll define a class of operators or class of kernels, and we'll say, well, we will cover them with an epsilon, positive epsilon radius, and we will want to know how many bits we need to extract on information on the system based on input-output traces, so that we can identify the system to within an error epsilon, okay? And here, as I said before, we work with LTI systems for conceptual reasons, simply because we do not know yet how to compute metric entropy of general pseudo-differential operators. I'm pretty sure that we have it, but I still need to tie up a few loose ends, and so that's why I'm not presenting it. But so this is now, the rest of the talk is for linear shift invariant systems, but it's more about the philosophy of system identification to within a certain limit. Okay, covering, you have a metric space, you have a compact set, you cover it by balls of radius epsilon, and you count the number of balls as a function of the radius epsilon. And the way I like to think about covering this as an encoder-decoder framework. In other words, you want to approximate elements in your compact set to within a certain error epsilon. So you have an encoder. The encoder maps an element in C to the closest ball center, xi. So that means the distance that is between xi and x is guaranteed to be less or equal than epsilon because we have an epsilon covering, and then encodes the index in a bit string. And the decoder, when presented with this bit string, can read out the ball center and produce an approximation to x, and the overall approximation area is going to be less or equal than epsilon, simply because you map to the closest ball center, you have an epsilon covering, and that's what it is. So the quantity of interest is the rate at which this big epsilon, which is actually the log to the base 2 of the covering number. So the number of bits you need to represent any element in C to within a certain error epsilon, at which this the rate at which this goes to infinity when epsilon goes to 0. Okay, so that would be, let's say, epsilon to the minus d for the class of Lipschitz functions mapping Rd to R, or in the example that I gave you about the real number in the interval 0, 1 is log 1 over epsilon. So, I mean, these are the tough ones. And if you see this, people usually shout curse of dimensionality. I'm not so sure it's such a fortunate term. If you see this, that's usually much easier, okay? So we'll be actually seeing that the systems that we are interested in, LTI systems, and we are going to look at exponentially decaying kernels, they will have log squared 1 over epsilon. So rather benign class to encode. Okay, good. So let's get started. So by the way, this viewpoint was actually put forward by Zames and Owen in '93, and then they had a series of papers about this. Papers are hardly cited, so I don't know why, but I find them beautiful. So if you're interested in this theory, I encourage you to have a look at that. So we're going to look at exponentially decaying kernels equipped with the operator metric. So the metric you can think of as follows. The system is a shift invariant system, so we know actually how to express the operator metric in the frequency domain. So when I write here rho of L and L prime is equal to sup x is equal to 1, Lx minus L prime x, this is actually equal, and then you have k L theta hat minus k L prime theta hat. And that's the Fourier transform, the discrete time Fourier transform. So k L of theta is the Fourier transform of the kernel. And then we have KL of n e to the minus I 2 pi n theta. So we look at the sup norm in the frequency domain, or in terms of interpretation, we look at a covering that is such that if you have a true kernel and then you use a covering center, then that would be L prime, then for any input signal or the worst case input signal, gives you a little L squared distance between the corresponding outputs that is no more than epsilon. Okay, so that's the norm that we equipped this with. And then what we have to compute is the covering number of this set here. Now we have exponential decay, and I'll be commenting on that later. I mean, you can actually be quite a bit more general, but this is just for concreteness. And the first result here by Zames and Owen is that the covering number is actually log 1 over epsilon raised to the power of 2. So that's actually, as I said before, that's fairly benign relative to epsilon to the minus d. Now, mind you, if you look at systems mapping Rd to R, you actually get a different behavior. Okay, so that's something that is important to emphasize here. Good. So what that means is that now we have our reference, and this is what we should target with our recurrent neural network. Just two comments. If A is larger, then the covering number is going to be larger, makes sense. And if B is smaller, the decay is slower, then the covering number is also going to increase. So the question is now, how can we achieve this covering with recurrent neural networks? And the way we're going to do this is we're going to quantize the recurrent neural networks. So there's two things you need to do if you want to encode a neural network or a recurrent neural network. You need to encode the topology. This is the locations of the non-zero weights, and you need to encode the real valued weights because real numbers have infinitely many bits to represent them. So you're going to quantize the weights and you're going to encode the topology. And here comes into play this constructiveness of the proof, where our constructions are such that the topology is independent. So the number of bits needed to encode the topology is independent of epsilon. So all we need to care about is how many bits as a function of epsilon do we need to devote to encoding the kernel. So we use uniform quantization to integer multiples of delta. And then we need to care about what Francis mentioned before, stability. So if you quantize, you don't want actually error accumulation because you have recurrence, okay? So all that nicely works out with that architecture. And indeed, you get the covering number. So let me show you a bit about the proof. It's on the one hand, fairly simple. On the other hand, it uses something that is quite crucial in terms of getting this covering number. So how do you identify a shift invariant system? You're excited by Dirac delta function or in discrete time by Kronecker delta, and that's it. And then you observe the output. So before I proceed to the proof interpretation, so RNNs give you an optimal epsilon covering of C of A and B with respect to the norm that we are looking at. They can optimally learn the class of LTI systems. Now, if you can optimally learn an LTI system, you can optimally learn an ODE, okay, or a difference equation, because we are in discrete time, and I'll be talking about that in a second. And this gives you a benchmark for practical learning algorithms. So here is how the proof goes. It has two elements. The impulse response is exponentially decaying. You need to choose a cutoff. So you're going to approximate your infinitely long kernel by a kernel of finite lengths, and you need to carefully select the cutoff point to be essentially 1 over b log a divided by epsilon plus some constant. The quantization level has to scale with epsilon. So each individual impulse response sample has to be quantized to integer multiples of delta, and delta has to scale like epsilon to the 2m. That also means, and then you use rounding. You can use seal or floor, it doesn't matter. But that also means that if you have, you explicitly use this exponential decay, and if you just use uniform quantization across all impulse response samples, meaning that you don't take into account, let's say, that you have exponential decay, and that as you proceed to the right, and you fix actually your quantization intervals, you do need to take into account that you have exponential decay. You cannot just do this here and then use whatever many bits you need for each of them. You need to exploit the exponential decay. How many bits do you need? Now, well, for M, this is, or let me just show you how many bits you need for each of those. The dynamic range, or the overall interval is minus a to the e minus bt and a times e to the minus bt. So that's log to the base 2 of 2a e minus bt divided by delta. Now you insert for this delta here. So that's log 2a e minus bt. And for this delta, you insert epsilon divided by 2m. And then here you get log a divided by epsilon. So that's the number of bits for each of those impulse response samples. And how many do you have? Well, you see it here. You have log a over epsilon. So you simply multiply log a over epsilon by log a over epsilon, and that gives you log a over epsilon squared. Okay, that's the proof. So the only important thing is that you actually adjust for this here. Okay, good. Now, finally, what does all this have to do with learning differential equations? So since we're in discrete time, we're going to look at difference equations. And what do we mean exactly by learning difference equations? So let's suppose you have a difference equation of this form, and you have the feed forward and the feedback part, and you have the AIs and the BIs and the P and the Q, and you have input-output pairs, so sequences X and Y, and you have finite resolution observations of the input-output pairs, And then what you can show is, again, for the system theorists, you will know this. If you take the Z transform of this to get the transfer function in the complex plane, and you assume that the system is stable, meaning all the poles are inside the unit circle, then you can actually show that the kernel is a linear combination of polynomials in T times cosine sine in T times an exponential decay. And then, of course, the exponential dominates the polynomial. And so this K is in our class that we looked at of exponential decaying kernels. And therefore, you can state that RNNs can learn stable shift invariant systems in a metric entropy optimal manner. Okay, yes.
So the lower bound for the metric entropy that you gave before, that is quoted from this other paper, this is over the class of all these operators of a certain kind. No, whereas when you have a differential operator, you actually have a specific subset of that class. So, so I'm not convinced when you say optimal, no, because you would have to show when you learn a particular heat operator, whatever, that your approximation is optimal for that class of objects, whereas your lower bound is just accrued over a general class of operators of a certain decay. And so the benchmark is not really a benchmark if you want. I mean, it could be that the PDE is much simpler and has much less metric capacity.
Yeah.
So how do you rule that out? I mean,
so here, that's why I said maybe I didn't read it. RNNs can learn stable systems. So what I mean by stable systems is that these are difference equations that if you take the Z transform of this equation up there, then you have a polynomial in Z minus 1 divided by a polynomial in Z minus 1. And then you look at the poles of this, or the zeros of the denominator polynomial. And if all those poles are inside the unit circle, then you actually have this condition here satisfied. So it falls into our class of kernels that are exponentially decaying with decay constants A and B. So A times e to the minus BT. So it's for this class that we have optimality. So now, of course, as you say, and I'm thankful that you reminded me, you can say now, well, can you do something more general than exponentially decaying? And yes, you can do something more general. You can have polynomial decay. Whenever you have this parameterized decay conditions, you can make things work out. But in this case here, the lower bound measures the upper bound is in that class of systems with exponentially decaying kernels. Okay, but I agree, whatever class you put forward, you would have to study the C, the correspondence to C, and then the computer's covering number, and show that you can achieve it with an RNN.
Just to clarify, if I understand it correctly, so when you say metric entropy optimal manner, it means that you are rate optimal.
Actually, even the constants we get in this case. So here, the result by there was actually, okay, there was a small accident when we wrote the paper. There was this issue about causality, non-causality, factor of 2, and so on. Yeah. And so it turns out that anyway, so yeah, we get the constant. So this is, where's the Zames result? It's here. And this little means there's a little o relative to log 1 over epsilon squared. And it's log to the base 2 of e divided by 2b log a divided by epsilon. And let's keep that in mind. And the RNN gives you exactly that. So it's not only the scaling, not only log 1 over epsilon squared, but even the constants are fine.
You say then you have from LTI system theory, you have this explicit functional form of the kernel. Yeah? Mm-hmm. And that guy does contain, for example, higher order polynomials. And how can you learn those with a ReLU activated net? Exactly, you assert exact. This epsilon is only from quantization, but you assert that this can be learned exactly.
Well, there is this little o term here, right? So that's what I'm saying, that it's all contained in the little o term here. And what we are, in terms of what you just said, we are here. So that's what we are using, that the exponential dominates the polynomials. And yes, lo and behold, it's all in the little o term. Okay, so then up to this little o term, right?
Then I'm with you, yeah, because ReLU cannot express.
No, I agree, right? But actually, it turns out, if you go through the proof, there is a lot of action of the kinds that you have in mind in the little o term. So there's a difference there.
Okay, then I'm with you. All right.
So Sven and then
I just had a question relating to Christos. So in your universal realization theorem, there's an exact representation, right?
Yes, right.
And so how does that, so for what kinds of difference operators does this hold? Like similarly to Christoph's question, because of the polynomials and the...
So the realization theorem applies to all linear descent in the sense of Charlie-Grachenic operators. Okay, so not only shift invariant, it's general. So your symbol can depend on X and omega proper. And we work with real valued weights, etc. So no condensation there.
Okay, so it could be multiplication by polynomial in Fourier space.
Multiplication by polynomial in Fourier space, that would mean you have derivatives in the time. Yes, of course.
Differential operator.
Yeah, true. Yeah.
Right. So that's also the way I introduced it shows that we represented some multiplication by polynomials in Fourier space, and then you go back and so on. So the answer is Richard.
Sorry, I don't want to, just because it's on the slide, I want to ask. So I mean, shouldn't, when you do a lower bound on covering numbers, shouldn't you prove the lower bound for all linear combinations of the form you've given there with coefficients theta and beta and so on? I mean, that would be the relevant lower bound if you want to learn this particular system, no? So it could be that for this, I mean, you kind of make this a subset of a more general class. And then for the general class, you have a lower bound for the metric entropy. And then you're kind of optimal with a reference to this more general class. But I mean, if I actually know that I want to learn something that is a linear combination of these things, I potentially could do better. That was my question before. So
Okay.
We can talk about this offline, but I wanted to sort of...
Yeah, no, I think that's a very good point. So what we did is, indeed, so I simply said that this is contained in the class we looked at before, and therefore it's fine, but we are being generous here. We're going to say, actually, if you know it's this here, so that could be, yeah, so relative to the, let's say, to the ambient class of impulse responses of exponential decay, which these guys happen to be in. But yes, I agree. If you know that you start with stable systems, so in that I agree with you, and I think this is a bit courageous. So I should correct the statement. And it's relative to C of A and B as defined before. You're fine, but within that class you could. But let me see if I can tell you anything about that. I'm pretty sure that it still is okay, given the proof and what we pushed into the little O term and so on. But I didn't have it in mind, so you're absolutely right to point it out.
In any case, even if the metric entropy is even better for this class,
Yeah.
your upper bound is a good one. I mean, it's a smaller metric entropy.
Sure.
Yeah.
It's just when you say
It's an
metric...
excellent start.
Yeah. But the Richard is absolutely right. The reason why I'm optimistic that it's fine is that, I mean, you excite the system by Dirac or Kronecker delta and so on. You observe the output. You do this here. And even if you know that it's P of T and so on and so forth, you can adjust the quantization levels. All you need to do is, adjust, this adjustment here. So I'm very positive that it's fine. But yes, the way it's stated, it's an ambient set, and you're right. Yeah. Good. So anyway, what are we doing now? Not yet in the Dolomites. Metric entropy rate. It was a Freudian slip, I think, with my. Metric entropy rate of general linear operators. So actually metric entropy rate and not metric entropy. So shift invariant systems, this is what I presented, but how do you do it for general linear operators? And there, as I said, we have a few loose ends to tie up, but you can actually show that for operators that, if you have a general linear operator with a certain Weil symbol, then it's not exactly diagonalized by Fourier functions. And then you have this whole underspread calculus that again is wonderfully exposed in Charlie-Grachenick's book. And then you can actually control the off-diagonal terms and make sure they don't dominate your error relative to the covering error. So it should work out, and you have to work with the notion of rate. So I'm pretty sure metric entropy for general linear operators should be fine. Now, nonlinear PDEs. For the nonlinear case, we have first results. Those are existence results. You can approximate every nonlinear PDE under technical conditions, either compact interval or you have this fading memory condition. And the way we do it is via lattice polynomials. Okay, so that's not written up yet or not officially, but that's that. And then reading out all these PDEs, I mentioned a lot. And so a general theory for this would be nice, like we have even for feedforward networks only for the hyperbolic tangent. but even for ReLU, it's difficult, as Remy also pointed out yesterday. And there's quite a bit of work in the continuous time case. Most of it is not explicit in terms of the structure that is behind it and so on. But there is very rich literature, starting with a nice paper by Funahashi and Nakamura, and then Matthews in '93, who I learned last week in Cambridge, was a PhD student at ETH, and Jim Messer encouraged him to write this paper, but then it received no reception at the time. So he left academia and did something else and so on. It's not cited also, but it's a wonderful paper if you have a chance to have a look at it. And then there's also more recent work. Okay, on that note, I would like to conclude and thank you very much for listening.